And in Sky at Night join forces to relay scientific and television history in the making, as Patrick Moore sets the scene for tonight's celestial encounter.
Good evening, and welcome to our Night of the Comet. Within the next hour or two, we may learn more about Halley's Comet, our most famous cosmic visitor, than we've done since the start of human history. I'm afraid you won't see the comet properly at the moment, but from the southern hemisphere, it's a wonderful sight, with its tail stretching across the sky. And here's the latest picture of it, seen from Siding Spring in Australia. Thanks to modern technology, we can now get close-range views of it. Whether we're going to see the actual nucleus is open to question, but whatever we do see will be of tremendous scientific interest and importance. The European Space Agency is sending its first deep space probe, Giotto, right into the heart of the comet. Something that's never been done before. This is a picture of Halley's Comet being sent back now by Giotto. Let me stress that those colours are not genuine. They indicate differences in brightness and therefore differences in density. And undoubtedly the mysterious icy nucleus is somewhere inside that patch that shows up on your screen as being blue. The object of tonight's mission is to follow Giotto all the way in. At the present moment, it's something like 250,000 kilometres away from the nucleus of the comet. At closest approach, in just over an hour's time, it'll only be 540 kilometres away. And it's then, if at all, that we're going to see the nucleus. We've simply got to wait and see. Halley's Comet is named in honour of the second Astronomer Royal, Edmund Halley. His headquarters was at Greenwich, at the Royal Greenwich Observatory, where James Burke now is. James.
Thank you, Patrick. Well, I'm here on what is a bitterly cold night at Greenwich because it was here, in a sense, where the original scientific interest in the Comet Halley really got going. And I'm here especially to look at the technology behind tonight's literally once-in-a-lifetime encounter, the encounter between the spacecraft Giotto and the comet called Halley. That we are able at all to rendezvous with a comet travelling at 68 kilometres a second, 230 million kilometres out in space, is mainly due to the original predictions by Edmund Halley, England's second Astronomer Royal, here some 300 years ago. The latest of his successors is with us tonight, here in the Octagon Room, where the earliest observations were made. Professor Sir Francis Graham-Smith, the 13th Astronomer Royal, is watching these events with his guests, who include Professor Alec Boxenberg, Director of the Royal Greenwich Observatory at Hurst-Wonslow, and other experts in what we'll loosely call tonight cometry. We'll be talking to them later. As Giotto races towards the encounter at about 70 times the speed of a bullet, I will be taking a look at the onboard instruments, and in particular at that camera that we hope will answer fundamental questions, not just about Halley, but perhaps about the origins of the solar system and even the origin of life on Earth. I say we hope for two good reasons. One, Giotto may not survive the journey to the heart of the comet to take those first ever pictures of its nucleus. And two, even if it does, the pictures that the two Russian spacecraft that went past the other day made it all look pretty dicey. The situation as they saw it makes us feel that tonight the encounter may turn out to be a more dangerous event than was perhaps foreseen. But more of those problems later on, because right now the spacecraft is heading into the comet's coma, a giant cloud of gas and dust surrounding the nucleus. And since Giotto's encounter speed is about 240,000 kilometers an hour, every tiny dust particle will hit Giotto like a bullet. This is what the spacecraft looks like as it heads for Halley, like this, with its dust shield forward. And as we go through the evening, I hope we will be able to see the build-up of computer-generated data showing the dust impacts actually hitting the shield at the time. The point is, will that dust shield work? Well, you'll be able to see the answer to that, as I said here, as the onboard impact sensors feed back second-by-second data on the kind of punishment that Giotto's taking. if the sensors themselves aren't destroyed, that is. Initially, that data and all the rest is coming in from space to a huge radio telescope in Australia and then to the European Space Operations Centre, Patrick.
Which is where I am now, at the headquarters of the European Space Agency. This is where the information from the comet is being received, but the real action is taking place over 90 million miles away. Here's the science area. We'll be meeting some of the principal investigators during the course of the night. And of course, there's the control room, which recently had the job of directing the spacecraft to its precise distance from the nucleus. But since the Russian and Japanese encounters, there's been a great deal of controversial discussion among the scientists here as to what that distance should be. We know that at the moment, Giotto is inside the coma, but outside the main dust area. What exactly is a comet? Basically, it has a nucleus, described as a dirty ice ball, which is the only reasonably massive part. When the ices are warmed, they start to evaporate, and the nucleus hides itself inside the head or coma, which is why we've never yet seen a cometary nucleus, something we'd like to rectify before this program's over. There are two types of tails. The plasma, or gas tail, is caused by the solar wind striking the comet's coma, the solar wind being a stream of electrified particles being sent out by the sun all the time in all directions. The dust tail is produced by the sun's light striking the coma and driving the dust particles outwards. And that's why comet tails always point more or less away from the sun. At the moment, Halley's comet is moving outwards, and so it's travelling tail first. The solar wind interacts with the cometary dust, and the solar wind is variable, gusty if you like, and this causes marked changes in the comet's tail. Giotto has already passed through the bow shock set up by the travelling comet, and we're getting ready for the main encounter. So let's consult the experts. What do they feel?
Well, I think this is the most exciting part of the mission. The spacecraft, of course, is now going to start seeing the dust. The instruments are now really going to start earning their money. The dust will start to increase significantly now, and it'll be starting to make the spacecraft wobble. So we hope we can maintain the signal, but at the same time we're hoping we can see the nucleus of the comet with the camera.
I'm hoping to see what the comet really looks like. So far, we've never really seen a comet. We've seen the dust cloud that envelops comets, and even those from a great distance.
We have preconceived ideas about the nature of comets. We believe that there is a comet nucleus in the center. We have some ideas about the origin of comets. We've worked for years on the composition of the gas and dusty atmosphere. We have pretty good ideas how much dust and gas to expect, but I'm sure there will be major surprises.
I am truly excited because it was 36 years ago that I first published my conclusions that the comet, the real comet, the nucleus, was made of ices and dust. And now we will be able to see what such a nucleus looks like.
Quite apart from the camera, Giotto carries many other experiments, most of them arranged on a necklace round the spacecraft. At the present moment, we can only speculate as to what a comet's made of. Giotto ought to tell us. We'll be studying the dust and the magnetic fields that are so important in tail production. We'll be looking at the chemistry and composition of the comet, its atoms, molecules, and ions, which are incomplete atoms. And then there are plasma studies. Plasma has been defined as the fourth state of matter, the others being solid, liquid, and gaseous, and is made of broken up pieces of atoms. But to demonstrate just what plasma is, let's go over to James Burke, or rather, see what James was doing in the courtyard of the old Royal Observatory a few hours ago when it was still daylight.
I'm doing it here in the freezing courtyard because, as you'll see, they didn't want to risk burning Greenwich down. Plasma, those broken up pieces of atoms that Patrick was talking about, make up about 90% of the universe. In this case, the plasma in question is caused by the solar wind, a cloud of superheated gas exploding at a million kilometers an hour out from the sun all the time. Now, the tremendous temperature of the sun strips the electrons from the gas atoms, and atoms without electrons are called ions. On board Giotto, the energy levels of those ions is being measured by a British experiment from the Mullard Space Science Laboratory. In essence, this is how the experiment works. This flame represents the hot gas plasma. And if you use this generator to send a charge through these plates and then through the ions in the flame, you can deflect the ions like this. Watch it being deflected to the left. It looks like wind, but in fact it's an electrical charge. Look, I'll do it again. And it's deflected. Now, if you measure how much charge causes how much deflection, you know how much energy the ions have, and you've measured the energy of the plasma. Now, that is basically how the plasma instrument on board Giotto works. This is where the plasma experiment sits on the spacecraft, and in fact it was switched on out in space some time back. The leader of the plasma analyzer experiment from Mullard is Alan Johnston. At his lab, he prepared his standby instrument for Giotto. This is the voltage generator. And these are the plates across which the electrical charge is applied. They're mounted on the particle detector itself. The plasma particles stream into the instrument and get bent towards the detector. Change the voltage, and you tune the instrument to measure the energy of different particles.
Well, some time ago, Giotto was hit by a huge shock wave. This is what it looked like on the computer printout. Let me stress that it didn't cause any damage because the density of the material is so low. Since then, within the last few hours, we've had some new information. Alan, what are your results so far?
Well, we've now been detecting the comet for more than 30 hours. We first found it at 4 o'clock yesterday afternoon, and it's gradually been increasing in intensity ever since then. And at about 8 o'clock this evening, we saw the first signs of the bow shock, and the bow shock turned out to be about 200,000 kilometers thick. And once we'd passed through the bow shock, we found, in fact, that it, instead of being more turbulent as I had expected, so far it's been quite a bit smoother, but hotter.
Well, you're using plenty of graphs. What exactly do they mean?
Well, we've got two to show on the screen here. This first one shows some of the different masses of ions that we're detecting in the comet. There's 4 frames there, each one taken successively, one after the other, in time, and each one shows hydrogen ions and alpha particles from the solar wind in the bottom left-hand corner, where it's red and green, and cometary ions in the top, where it's blue. And one of the interesting things is that we're seeing particles at a mass of 8, where we didn't expect to see them.
How do you assess your results?
Well, they're very interesting. They're going to take a lot of analysing, but they're extremely interesting.
I imagine you expect better results from this as Giotto closes in toward the comet?
Yes, we're expecting things to change very rapidly in the next hour, and especially in the last 2 or 3 minutes just past midnight.
Alan, thank you very much. One thing that happens in comets is that the sunlight breaks up the molecules in the coma. Now, the comet's gravity is too weak to hold them down, so they start to drift away from the coma. Then they meet the solar wind, and they are hurled back into the coma. So one of the experiments carried upon Giotto is a detector to pick up these so-called energetic particles.
The Irish energetic particle detector is just here. It consists of 3 tiny telescopes collecting particles that are analysed by a solid-state detector at the back of each scope. Now, 2 of those scopes face sort of forwards, and the other one, well, it faces backwards. That isn't just an Irish way of doing things. It just doesn't matter which way you point when you're dealing with those high-energy particles. Moreover, many scientists didn't really think there'd be much call for such an experiment to measure them, so it wasn't originally going to go at all. But it is very small, it doesn't require any power supply, and it has a very persuasive Irish scientist who made quite certain it got on board.
How's the experiment going?
It's going very well. I'm pleased to tell you we have superb performance from the instrument.
What are you looking for?
At the moment we're looking for 2 things. We're looking for electrons which come from a hot plasma source associated with the comet. So they should come in puffs along the interplanetary magnetic field line when there's good connection between the comet and the instrument. So we'll be seeing those here. In fact, you can see some of the counts building up at this moment in those channels. And then another thing that we're looking for are pickup ions in the solar wind. You know that when the particles are ionized and become charged, they spiral around the interplanetary magnetic field line, so they can actually pick up energy from the solar wind.
And of course, if Giotto survives, you'll be able to go on collecting data on the outward journey.
Oh, well, that would be absolutely splendid, you see, because if that happens, then we'll see the pickup ions again on the other side, and we can go on observing for quite a long time, so the outward pass will be just as exciting as the inward pass.
There's another particle experiment which is British, and this has to do with the density of the dust. It's fascinating, but it does raise a problem, because it's this dust which is the greatest threat to Giotto's survival. James.
Well, there's now less than an hour to go and 231,600 kilometers to go to closest approach. As you can see on the left, there's time to go to the closest point, and on the right, the distance. And from here on, from this distance out, to the problem of dust becomes the major test of the mission. The first impacts from the dust cloud in the coma around Halley were predicted to start just a few minutes ago, and we've heard that that's exactly what's happened. Let me remind you of what's happening out there in space. Giotto is heading in towards Halley like this, with its protective dust shield forward, and I'll get back to that particular dust shield in a second. There you can see it spinning around with the dust shield leading. Now, the theory is that the dust I'm talking about happens as a result of the sunlight evaporating the icy surface of the nucleus of the comet and the explosion of superheated gas pockets in that surface, sending the dust shooting out in great fountains to spread perhaps as far as, 100,000 kilometers out round Halley. I say it's all theory because nobody knows. That's one of the things we're hoping to find out tonight. But the size of the dust particles in that maelstrom are known. They're anywhere from this size, the size of a dried pea, right down through sand grain size to tiny particles this size, so small that they almost smudge when you move them around, and beyond that to the size of the particles in the smoke from a cigarette. Now, those dust particles are killers for two reasons. The first is communication. You see, the main spacecraft antenna, this dish here, is sending all the data and the pictures back to the receiving dish in Australia, back on Earth, 130 million kilometers away. Now, the distance involved in that communications link is so great that it needs pinpoint accuracy for the antenna to make and maintain contact. 1 degree off, that much, and we lose contact. And an impact from one particle this size hitting the edge of the spacecraft could knock Giotto off-center enough for the signal beam to miss the Earth. The second danger to the spacecraft is less, shall we say, subtle. Particle impact could just destroy Giotto. That's why there is a dust shield, or rather, two of them. An outer shield here, 1 millimeter thick, made of aluminium alloy, like this. And an inner sheet, 25 millimeters behind it, itself 12.5 millimeters thick, a backup shield made mostly of bulletproof plastic laminate to take the force of the particles that are big enough to smash through the outer shield and hit this inner shield like in the form of a jet of high-temperature vaporized material. And they're expecting plenty of that kind of activity. In fact, at worst, all the spacecraft has to do is just survive through that dust storm long enough to get in really close to the nucleus to snatch its pictures and scientific data before it is possibly destroyed. And if you think I'm overdoing the drama bit, take a look at this. This is a piece of test material looking at the conditions that forward shield would encounter, the thin aluminium shield. It's been scaled up because they can't shoot a pellet as fast as the spacecraft is going, so the whole thing's scaled up. This was made by a pea-sized object fired at 5 kilometers a second at this aluminium 8 centimeters thick, 8 millimeters thick. That is the same scaled-up effect of one pea-sized object hitting the forward shield, that thin 1 millimeter thick shield. Now, they're expecting many, many of these impacts, perhaps as many as 10,000 a second. The second test they ran was on the Kevlar, as it's called, the Kevlar backup shield, and here they used a laser to produce the kind of effect that the jet of high-temperature plasma coming from the result of a particle having smashed through the front shield, the effect it would have on the Kevlar. And as a matter of interest, over here on the edge, there's a tiny detector. There are several of them around, as you'll see soon, that actually detect those impacts happening. And that was I was talking about when you were looking at the screen on which we will be able to show you the effect of those impacts as they happen because of computer generation. The key point encounter, as you can see on the countdown, will happen 51 minutes, just under 51 minutes, and 213,000 kilometers from now. There are, as you would expect, from what I've said about the dust, several experiments on board measuring those impacts. 2 experiments registering impacts by the very small particles, and one run by the University of Kent for the bits large enough to call what they're expecting to make real trouble. Tony MacDonald leads this British experiment. It's called the Dust Impact Detector, or DID. Giotto's leading surface carries 3 tiny sensors. The inner shield carries one more. The sensors are miniature microphones to record the impact of particles hitting Giotto faster than a bullet. McDonald's main problem is that he doesn't know just how big the particles will be. And will the twin shields be enough to protect Giotto? He tests the system with tiny glass beads. The mini microphones record the impacts, telling McDonald the size and position of Halley's dusty missiles.
At the moment, the experiment's going very well. We're getting a high-level activity on the front dust shield, and this is showing that some of the particles are going through to the rear, and it does show that the meteoroid protection system is working. Looking at the next few minutes, we're going to find the activity increasing and several thousand per second later. What's important is that we get through the point of closest approach and come out of the comet on the other side.
So you see there from what Tony McDonald was saying, they're already getting impacts that are going through that front shield. By the way, it's called the sacrificial shield, and now you know why, because even this far out, what, 206,000 kilometers with 50 minutes to go, they're beginning to get impacts going clear through that front shield. Well, the predictions are, in fact, that they will hit a fair amount of these medium-sized particles early on, and then hopefully the impact rates ought to drop off a bit before those rates start to rise inexorably towards maximum density as we move towards encounter. Question is, will Giotto survive long enough to get close enough to learn something about what that nucleus is made of? Patrick.
The nucleus is, after all, the heart of the comet, and that's what the scientists here are trying to study above all else. Up to now, we've been reduced to little more than guesswork. Some years ago, it was thought that a comet might be a flying gravel bank. But now there's good circumstantial evidence that the nucleus is an icy mass, about 6 kilometers in diameter, spinning round in something like 54 hours. If we knew the size of the nucleus, we could work out its mass and its volume, and we could then estimate how long Halley's comet will last before all its ices are used up. And present estimates range between 50,000 and 200,000 years. The camera was switched on again for the encounter 5 hours ago, and this is the best picture it's sent back so far. Well, dust or no dust, the camera is certainly sending back results, and there's quite a difference between this picture and the last one you saw. Now remember, Giotto is approaching the comet at something like 68 kilometers per second, and that makes a tremendous difference even over short periods. And now we can actually start to see structure in the comet. Once again, let me remind you that these colors are not real. They indicate differences in brightness and therefore differences in density, and there's no doubt that the densest and brightest part of the comet is that white blob you can see at the bottom, and that is where the nucleus is, even though we can't actually see the nucleus itself at the present moment. And then red, blue, green and purple indicate lower and lower light levels. So at the present moment, the camera is sending back good results. And of course, as it goes in closer and closer, we shall get better and better results. And one thing we know for certain now, the camera itself is working really well. James.
Well, this is where the camera sits, with its mirror poking out from behind the dust shield. That camera's job, of course, is to detect the nucleus and then take as many colour pictures of it as it can. The delicate camera is Giotto's most immediately dramatic experiment. Already it's sending back a continuous stream of pictures. This is Giotto's eye, giving scientists the chance to see a comet's nucleus. The camera can be rotated to take pictures both ahead and behind Giotto as the spacecraft skims close to Halley. The hope is that the camera will survive the dust storm, mounted as it is behind the bumper shield. Its pictures in 4 colors allow scientists to establish the size and shape of Halley's nucleus. From 500 kilometers away, the camera can pinpoint an object a mere 30 meters across on the comet's surface. All this while Giotto itself is spinning 4 times a second. Incoming light, and maybe dust, bounces off a steel mirror into a telescope. The image is then focused onto 2 charge-coupled devices, or CCDs, which take the picture. This is what the charge couple device looks like. Hundreds of lines of light-sensitive spots, and as the spacecraft rolls, I'll use my finger to imitate that, and the image moves across the camera mirror, one thin cross-section of the image at a time is stored on here for a few microseconds, and the data sent back to Earth. And then the next line, and so on. It's hairy stuff, but that's quite a camera. I mean, it could, for instance, get a clear shot, they say, of a mole on the face of the pilot of a Concorde going by a mile away at the speed of sound, which is great if the Concorde isn't in the middle of a cloud, which, according to last week's Russian pictures, Halley is. Now, from 8,000 or 9,000 kilometers, the Russians weren't expected to see the nucleus. Even so, the cloud they did see looked very small and very dense. When all the Darmstadt scientists got together to discuss that particular matter, all hell let loose. Some wanted to send Giotto very much closer than the planned 500 kilometers. But the camera team naturally wanted to play it safe and steer clear to over 1,000 kilometers away from anything that would sandblast the motor of their camera. With 2 or 3 times as many camera scientists occupying far more space than any other experiment, it would have made it a waste of money to build a spacecraft that could go to half that distance, to 500 kilometers. So in the best European tradition, they compromised. They chose a target distance the other day of 540 kilometers, almost exactly what had been originally intended. Just now, as you can see, the distance to go is 185,000 kilometers with just under 45 minutes, and closing. What are the pictures like from this distance? Patrick?
Well, they're pretty good, and the camera is working very well. But one thing we have got to remember, as Giotto goes into closest approach, it makes a very, very rapid pass of the nucleus, only about 10 seconds or so. And altogether, Giotto spends only about 4 minutes closer into the nucleus than Vega did. So it's got to be a very fast business altogether. But all the same, they seem fairly confident that they will get better pictures than Vega obtained. The procedure, by the way, is for Giotto to send back a raw picture, and then after a few minutes, it's enhanced, so you get a bigger and better view of it. And that's the way it is done, and all the pictures you're going to get tonight will be on this false colour principle. And I say again, the colours are not genuine. But already the comet is showing structure, and as we get closer and closer to the nucleus, there's no doubt at all that these pictures will gradually improve. So is the nucleus really a dirty snowball? That was the theory put forward by Dr. Fred Whipple over 30 years ago. You're still confident about it?
I certainly am. I think we have a great deal of evidence to prove that it is true. Particularly radar observations, radio reflections from the nuclei of 4 comets showing that there is a discrete body in each one of them.
What evidence are you looking for from Giotto?
Well, particularly the shape and the surface characteristics of the nucleus, because so far this has been entirely a matter of imagination. Now we will see the real thing.
So you're really hoping to see the nucleus tonight?
I'm really expecting to see it tonight.
Well, some people suggested that we won't because it'll be hidden by dust.
Well, there will be some loss of visibility due to dust. There's no doubt of that. But I think that because of the protection that the camera has in Giotto, there's a good chance that we shall see at least some details of the nucleus.
If we're going to make really close-range studies of the nucleus, the first thing we have to decide is exactly where the nucleus is. And remember, it's well and truly hidden by the dust. There's another complication also, the jet problem. Gases escaping from the nucleus which push it around and may also be a hazard to Giotto. Dr. Rudiger Reinhardt, could they possibly endanger the Giotto mission?
They could very well endanger the Giotto mission, although one has to say that the dust jets as we see them consist of dust particles in the range of 1 to 10 microns. These particles are of no danger to the Giotto spacecraft. However, associated with these visible jets are regions of dust particles which are not visible, large dust particles, and these could endanger the Giotto mission.
Could they put it off course?
Not off course, but they could disturb the spacecraft attitude, and then the telecommunications linked to the Earth could no longer be maintained.
Well, here I am with the guests. Sir Francis, you've been watching what's happening so far and listening to the people in Darmstadt sounding as if everything seems to be nominal, although those pictures are quite remarkable. What do you think about the chances of the mission?
Oh, that's just sheer speculation. I'm just sitting here and enjoying the atmosphere of the whole occasion. I mean, here we are sitting in the room where Halley worked for 20 years or so, I'm seeing on the monitor people like Jan Oort and Fred Whipple, who have done so much, if you like, speculation, but marvelous ideas, marvelous theories about the comet. And we're just sitting here waiting for it to happen. I think it's wonderful.
Yes, it is, as we've said already, of course. It's a once in a lifetime for almost all of us, isn't it? Professor Meadows, this business about the dust, it doesn't seem, it seems to have been a bit of a blip and then it's quietened down. Is that what you would have expected?
Well, like Graham, I'm in a coma. Sort of, I think, is the answer. If you look at the Vega results, which you've seen earlier, yes, they were actually somewhat discordant, and the problem is that the theme tune for any comet is ashes to ashes, dust to dust, hurry on baby, you must, if you follow me.
That's a technical statement.
It's a technical statement, which will be published in due course. The problem is that they're erratic. They give out stuff. You were talking about jets there a little while ago. The problem is you get these jets erratically, you can't predict them.
Yes.
And the stuff you can see is the smaller stuff, ground-based. Unfortunately, ground-based, you can't see the larger stuff, and that's the dangerous stuff. Which
and
is
in fact, there've been, I mean, a number of impacts through the front shield already.
Already, indeed. The problem is the size distribution can't be accurately predicted from Earth because you only see a part of it.
So you can't, you can't fully prepare for it. In other words, they can put up a sacrificial shield, but presumably it is impossible to say that a large enough particle will not come along that will go right through the spacecraft.
Spot on, right.
I mean, is that possible?
Oh, of course it is, yes.
And you have no way of predicting?
No, because where you're dealing with small, with a small number of large particles, then you're dealing with small number statistics and you cross your fingers.
Yes, sure. And there's a lot of space out there. Let me turn to Alec Boxenberg. You kind of pioneered means of seeing clearly at great distances in space with your work on the image intensifying systems earlier in the last decade, in the middle of the 70s. What's your view of the pictures coming in now?
Well, they're remarkable pictures. The device that's used is the charge coupled device that you mentioned. Yes. Now, that has an extremely large dynamic range, and of course is very sensitive and has a very wide colour response. And all those things coupled to give immensely high quality. But of course you can't see that necessarily immediately. Yes. These pictures have to be massaged.
You think we'll get a good picture of the nucleus if it gets to see it?
Well, I think we'll get a good picture eventually. We may not see that tonight, but we will be able to massage that picture and see it eventually, I'm sure.
Good. Thank you very much indeed. I'll come back to you, of course, later on as the mission proceeds and we discover that everything you've said is wrong, all of you, including us. Let me go on now to talk a bit about the origin of comets, because where comets actually come from has always fascinated astronomers from long before the time of even Halley himself.
Whence come the comets? We believe they come from a whole cloud of dirty ice balls circling the sun at a distance of perhaps a light year. And that's a long way. If you represent the Earth-Sun distance by 1 inch, a light year is going to be 1 mile. If one of these dirty ice balls is disturbed for any reason, it starts to fall inward toward the sun. If it's not caught by the gravitational pull of a planet, it'll simply swing round the sun and then return to the Oort cloud, not to be seen again for a very long time indeed. But if it is caught by the gravitational pull of a planet, generally Jupiter, then it may be forced into a short period orbit, as Halley's comet has been. The man who first summarized these ideas was Dr. Jan Oort, after whom the cloud is named. Dr. Oort, has anything recently made you change your views at all?
No, not really. There has been some criticism, but I don't think it really counts, the criticism. And,
What's the special significance of Halley's comet as a relative newcomer from the Oort cloud?
Well, it has come in from the Oort cloud a long time ago, many thousand years, and has made several thousand revolutions probably already. So in that manner, it isn't. It has changed its constitution from what it was before, when it lived quietly in this distant cloud.
Almost all astronomers now accept the idea of the Oort cloud, and that's also true of the dirty snowball theory, which of course is due to Dr. Fred Whipple. What evidence are you looking for from Giotto?
Well, particularly the shape and the surface characteristics of the nucleus, because so far this has been entirely a matter of imagination. Now we will see the real thing.
So you're really hoping to see the nucleus tonight?
I'm really expecting to see it tonight.
Halley's Comet has been selected for a number of cometary missions because it is the only comet among more than 1,000 known comets which has both a well-known orbit and at the same time a high activity.
Giotto itself, of course, is essentially a European mission, but the Europeans have had some help initially from an American spacecraft that some time back went to visit the tail region of a comet called Giacobini's Inner and produced, obviously, information that was useful, although, as you heard Professor Meadows say, that might not bear any relation to what will happen to Giotto tonight, such as the unpredictable nature of what's happening. But at least the Americans provided some information. However, in this case, that spacecraft will continue, but will only approach to within, about 32 million kilometers of Halley and arrive 3 weeks after the rest of the international team. Pathfinders for this mission, though, were the Russians. The Russians launched their Vega 1 space probe in mid-December 1984, and Vega 2 6 days later. The start of a 14-month journey to take the Vegas to within 9,000 kilometers of Halley. The slim solid-fuel rocket carrying Japan's second Halley mission stood ready for liftoff last August. For the Japanese, Project Halley is the first venture into interplanetary space. Their main spacecraft was aimed to pass 150,000 kilometers from the comet's nucleus. The Japanese Planet A spacecraft's mission to monitor the comet's vast ultraviolet corona. The European spacecraft, Giotto, is by far the most ambitious of the multinational group. Tonight's encounter comes at the end of a journey that started last July in Kourou, French Guiana. Sited near the equator for maximum benefit from the Earth's rotation at liftoff, the Kourou launch pad is the home of ESA's Ariane rockets. Giotto was to be carried on the first stage of her 700 million kilometer space journey by Ariane flight number 14. July the 1st, launch day -1, halfway through the long countdown procedure. Ariane is ready to go. For Giotto's scientists, 5 years' work now rests with the Ariane launch engineers, and Ariane rockets had been known to fail in the past.
Plus 3,4 secondes, l'ouverture des crochets, suivi du décollage.
First stage servo motor started.
Les paramètres et les mesures sont actuellement corrects.
Attention, bourrage 0. Final arming, ready to go.
Les derniers armements ont lieu en ce moment.
10, 9,
Décompte final.
8, 7, 6, 5, 4, 3, 2, 1, top. Ignition. Ariane first stage ignition and takeoff. Takeoff and décollage. First stage flight. Début des manœuvres de roue libre.
Safely on course. The Japanese Planet A arrived 5 days ago, closing with the comet at over 70 kilometers a second and successfully measuring Halley's ultraviolet output. The Russian Vegas moved in last Thursday and Sunday, sending back pictures and pinpointing Halley's precise position. The Vegas narrowed down the path of Halley's orbit by a factor of 3. So, Giotto is being guided with amazing accuracy for the closest encounter. Tonight sees the culmination of that mission as the small spacecraft spins the last kilometers towards the comet's very heart. Just a few moments from now, Giotto meets Halley. So, how did the Pathfinders get on? the Russian Vega spacecraft are vital to the success of the International Halley mission as a whole, and of course for Giotto in particular. Patrick.
Both the Russian probes, the Vegas, have been very successful. They're also of tremendous value in the Giotto mission, because now we have at least some idea of what to expect. Both the Vegas bypassed the comet between 8,000 and 9,000 kilometers. The instruments recorded strong electric fields and electron currents. The plasma density was measured, and there were indications of a tight inner dust shell. Vega 2 took some fascinating pictures. Look at this. It seems rather like a double nucleus, although there must presumably be some sort of connection between them if it really is a double nucleus. Let's hope Giotto will tell us more. But there's always the dust striking the spacecraft at 68 kilometers per second, and it did do some damage. Remember, though, that the Vegas weren't equipped with dust shields, anything like so efficient as Giotto's, so they were much more vulnerable. Dr. Sagdiev, did you actually see the nucleus?
I hope so. We have seen the structure of the region, which scales within only a few kilometers, and nucleus is certainly there. But probably we have to redefine what nucleus really is. It's not, it doesn't look like solid rock. It looks like something of sophisticated, maybe double structure, and the edges of this object are completely made obscure because of probably a lot of dust streams and jets.
What about the comparison of Vega 1 and Vega 2?
The first impression is that Vega 1 and Vega 2 had encountered different comets. The reason why it's so, we have confirmation from different experiments that Comet was much more active during the first encounter. It was much more dusty with jets, and one spacecraft entered inside extremely dense jet, and number of counts for the dust particle impacts went up more than an order of magnitude.
Were you disappointed that some of the instruments were damaged by the dust?
In principle, we were ready for kamikaze mission. And my personal judgment was that we were very lucky to come in such a condition. We certainly have lost a few experiments, and we have lost more than 50% of solar panels, but still it's okay. I think it gives a very good hope for Giotto to go through at much closer distance and to be alive.
Well, Giotto was always designed to fly by relatively close to the nucleus, so we carry a dust protection shield, and all the instruments are behind that dust protection shield, apart from the experiment apertures. Vega was designed to fly by at 8,000 to 10,000, so they carry less dust protection.
How much dust would you expect?
According to some of our models, about 3,000 particles in the intermediate size ranges per square meter and second. So there will be a lot less dust at larger sizes and a lot more dust at smaller sizes.
The camera seems to be dictating the target distance.
That is correct. The camera cannot rotate fast enough. There are some experiments which would like to go closer to the nucleus, like the neutral mass spectrometer. That experiment would like to see some exotic parent molecules with rather short lifetimes. And there's also a group of experiments which don't really mind whether they go a little bit closer or a little bit further away.
Now, the Japanese have been getting a great deal less publicity for their encounters, but they too have been getting some extremely interesting results. At the Institute for Space and Aeronautical Science in Tokyo, results from the twin Japanese spacecraft have been coming in since mid-December. Spacecraft Sakigake has been measuring Halley's interaction with the solar wind from a distance of 7 million kilometers, while spacecraft Planet A has been taking ultraviolet pictures of the comet's hydrogen corona. The UV pictures confirm that Halley's hydrogen cloud is over 2 million kilometers across, and that the comet rotates once every 53 hours. But in addition to that, they say it looks as though one side of the comet's very much more active than the other, throwing out perhaps up to 50 tons of material a second compared with only 20 on the less active side. They even suggest that on the active side there might be some sort of crack or groove, and that might be where much of the dust is coming from. According to the story, the two Vega spacecraft passed when the active side was facing towards them, but for Giotto's encounter, the less active side should be turned towards it, and that should be improving its chances of survival. That might well be why we are hearing, although Giotto's position is still much further out than the Vega's at their closest, why we're hearing that there are reports at 107,400 kilometers from the nucleus, give or take a bit, that we're still only getting reports of small amounts of small particles. Professor Meadows, what do you reckon to that?
Yes, I think that's right. The forerunners have been very helpful in seeing which way things are going. The Japanese result you mentioned, there's also the question, of course, that the nucleus is rotating, and preferentially the jets often seem to come out along the equator of the nucleus rather than up the poles, and Giotto is fortunately not in the equator, so it should avoid things with any luck from that viewpoint.
Thank you. Let's go back to Patrick in case there's more update information coming from Darmstadt right now. Patrick?
Well, we're delighted that Susan McKenna-Lawler has been able to join us. Susan, how are you getting on with your energetic particles?
Oh, it's a great success, Patrick. It's really going very well indeed. Instruments still working superbly. I've just brought you some very rough and ready results coming straight off the presses. I thought you might first like to see our first view of the comet. I think it's on screen now. And do you see that rise there in the right-hand corner? Well, that was our first view of the comet, 45 to 76 keV particles at 10 o'clock last night. Now, when I talked to you earlier, I rather knew about that, but we wanted to confirm it. But that's our first view of the comet, and we were one of the first experiments to detect Comet Halley.
What other special results have you?
Well, the next one that I'm really very excited about is the next picture. The bow shock was crossed, or the bow wave, really, we would prefer to call it, was crossed at about 1940. And look at those tremendous accelerations of particles at 78 to 213 keV, 45 to 76 keV. You know, this is very, very interesting indeed, very interesting theoretically, and I think this is due to acceleration which is taking place in that transition region.
Well, it is certainly a very worthwhile experiment. Susan, thank you very much. You've also been joined by David Dale, who is the project manager of Giotto. David, how's the spacecraft running?
Well, so far, running extremely well. We had no failures at all. All the ground stations are operating perfectly. All the lines from Australia are operating perfectly. All the people in the control room are very relaxed. We have seen the first dust particles on the front of the spacecraft, but there's been no attitude perturbation at all, so at the moment we're in no dangers. But of course now we are entering the region where the dust is going to build up. And in a few minutes, or a few seconds in fact, I'm going to go down to the main control room and see what the activity is there. But to date, everything is working perfectly.
That's good. David, thank you very much.
Thank you.
Well, Giotto is speeding its way through the coma on its way to the nucleus. And we may be on the verge of finding out what a comet is really like. And that's not only interesting, it's also very important, because a comet is a very ancient thing, and learning more about it may tell us more about the back history of our own solar system, including the Earth. Because we believe that comets are icy remnants, left over, so to speak, when the main planets were formed. And they haven't really changed much since then, apart from the fact that they lose a certain amount of their material every time they come round the sun to form the coma and the tail. And the coma is formed by the ices in the nucleus sublimating. And by that I mean changing direct from the solid to the gaseous form without going through the liquid stage. But what kind of ice is it? Ordinary water ice certainly predominates, but there may be other ices too. For example, methane ice or solidified methane. And that's what we want to find out. And Giotto is our best hope because it's up there now carrying out an on-the-spot survey. James.
Well, you can see what a comet's coma is made of with a telescope from Earth, for example, by analysing the spectrum of the light coming off it. They did quite a lot of that kind of work the last time Halley was here in 1910. The trouble is with that kind of technique, what you're looking at is atoms of the original molecules of gas and dust split up by the sun's ultraviolet radiation and in some cases recombined into different molecules. For example, this picture was taken from Table Mountain in California and shows the comet's positively charged carbon monoxide. And this one, coming now, is cyanogen, or cyanide. Matter of fact, it was that which in 1910 made people think that they were going to be poisoned when the Earth went through the comet's tail. But even the latest earthbound observations like those are still showing you, so to speak, second-generation molecules. The only way to get at the original parent molecules, as they're called, and to find out, therefore, what the nucleus is actually made of, is to be there like Giotto is. At least we hope it will be. And right now, there are 2 onboard instruments looking for those parent molecules and at the composition of the dust particles as Giotto moves deeper and deeper into the coma. The first is the particle impact analyzer. Incoming dust particles are detected on a target and split into ions. They're accelerated into an angled tube. And the lightest arrives first. Their flight time is a measure of their mass. The second experiment measures positive ions. Ions are deflected in a curved magnet onto a target plate. Where they fall on the plate tells you their mass.
And now for some views of the ion mass spectrometer, and we're delighted that Dr. Johannes Geis has joined us. Dr. Geis, how's it going?
It's going very well. We are, of course, very eager to get as close to the nucleus as possible. We're just getting a number of different ions, carbon, oxygen, fragments of water ions, and of course they will increase tremendously if we get closer, safely closer to the nucleus.
Well, you wanted to go very close to the nucleus, and indeed you were prepared to risk an impact to destroy the spacecraft. I think that was worth it?
Yes, so far we seem to be right, because the spacecraft is still alive. We want to go so close because the molecules which come out of the evaporation of the nucleus, they are rather fast split up by solar light, ultraviolet light. And the closer you get to original molecules. And that's very important to calculate back what you have had in the nucleus.
When can you start getting very useful results? It should be any moment now as the spacecraft
Even now we have them, and it will of course increasingly be more useful, and we will have a lot of ions. We even have now half a dozen, and there will be more.
So you think on the whole that it's worth it? The chemistry is more valuable than pictures?
Well, I would say they both come together, you know, but certainly the chemistry is very important because these volatile elements, we don't find them in meteorites in large numbers. It's important to see what the ice is made of, water, and you may have organics. Carbon ions we see, so there must be some organic material, yes, but we don't know yet what it is.
Thank you very much, Dr. Geis.
Thank you.
Well, the situation with the dust impact detector is that we're getting a reading on the average rate at which the particles are hitting. They're still small, and the rate is still relatively low. Sometimes, of course, some of the people that one talks to would say that would give you more cause for concern because it's anomalous. I mean, it's a hole where you'd expect something to be happening. The trouble, as Professor Meadows said earlier about this whole thing, is that nobody knows what's going to happen until it happens. And that's why, to a certain extent, this entire program is a sort of very fast preparation for a very short period of intense activity, which is precisely, of course, what the scientists have been doing for some years, because when Giotto makes its closest encounter, its closest approach, if it survives, it's going to flash by that thing very fast. There's too much danger of what could happen because of the eventual build-up of dust, so there's no recording mechanism on board. So, as some of the scientists themselves have described what's going on, it's going to be very much instant science, instant picture, and instant reaction. And everyone is really waiting, preparing, building up for the moment so that when it happens, they can interpret it as fast as possible, and I hope that means that for you we can do the same thing. Speaking of fast interpretation, Dr. Jim Cohen, your particular field is not one of your particular fields, let's say, is coma chemistry. Is there anything you're hearing tonight that surprises you, tells you anything that we might expect later on this evening about what's going to happen?
Well, the real interest is going to be in the very last few seconds, because most of the chemicals which are studied...
What do you mean by study, sorry?
Well, we do radio work, looking at the whole emission from the comet. But, of course, we're only looking at, in many cases, broken up fragments of the most interesting molecules of all, those coming right off the comet itself. And it's only going to be in the last few seconds, really, that Giotto penetrates into the very central layer, where, beyond the sort of contact discontinuity, where you're looking at material which has not been got at all by the sun, material just fresh off the comet. And that's really at that point where the most interest will be in
I mean,
finding what those molecules are.
Do you feel the same way as Jack Meadows, that in your particular area, that there's no way that you can tell what that's going to be like until it happens? In other words, all comets, as it were, are anomalous. There's no rule that fits all of them, and therefore you can't tell in your particular area, for example, that there's a certain build-up, there's a certain tendency, and therefore you could expect certain things. You're still guessing all the way.
Very much so, yes. We're looking at we hope, just fragments of really much more interesting, much more complicated molecules. We might learn something about those tonight.
And Professor Boxenberg, are you, in a sense, capable of helping the chemistry people by getting the kinds of images that will give them any kind of clue at all, or is it still all guesswork? You look up there and you say, well, we're getting second generation molecules, we can't have any idea of what they could be. There must be some trail, theoretical trail, back to an original parent that you can guess and then specifically look for.
Yes, of course, the techniques that one uses in just getting images aren't really that sophisticated. You need to get another instrument in line, a spectroscope or something like that. But nevertheless, from the images one can get some good guesses. We may get that tonight.
But again, it will all happen in the very last few minutes.
Yes.
Okay, let's go back to Patrick and see if we're any closer to knowing anything in advance from Darmstadt. Patrick?
Well, in point of fact, we're now within a very few minutes of closed-in countdown by entering the most exciting time of all. Let me show you how they enhance the pictures. The picture comes through, and then it can be jacked up like this, and to bring out the detail, as you can see. So the raw picture that comes in bears only a little resemblance to what you finally get. The picture can be improved by out of all recognition. And that is, in fact, how it's done. And another picture has just come in. Look at that. Once again, this is a false colour picture, and that red blob must indicate the position of the nucleus. And before very long now, we shall know exactly what that nucleus is. And Giotto at the moment is still going. It's still going, and we're very close now to the vital moment as it speeds inside and makes its closest pass of the nucleus. James?
Well, I mean, it's evident that what we're doing is moving in towards what, in the models before the mission even began, we are moments away from that predicted dust storm that hasn't occurred. So whether or not it's going to come, as Jack Meadows says, suddenly, out of the blue, unexpectedly, and therefore a situation for which you can't prepare yourself, isn't it perhaps time to take a quick look at the spacecraft itself to see what it's made of? After all, given the situation right now, it may be the last glimpse that we ever have of it.
Giotto has been spinning through space once every 4 seconds. Its main antenna dish has to remain stationary, beamed constantly towards Earth. Only in this way can the regular stream of pictures and data be maintained. Largely tested in France, Giotto was built by a European consortium led by British Aerospace. The spacecraft is basically barrel-shaped, most experiments and delicate parts housed inside. Throughout its 8-month-long journey, Giotto has been powered by these solar panels placed around the spacecraft's outer wall. And hydrazine fuel tanks feed thruster motors to shift attitude and trajectory in flight. Giotto's quite small for such an immense journey, standing barely 3 meters from base to antenna tip. At the core lies the solid fuel motor that blasted Giotto out of Earth orbit. The structure consists of 3 platforms topped by a tripod. The 2 dust shields and the scientific experiments are housed below the central platform. And under the tripod, the radio antennae to beam that data back to Earth. Altogether, Giotto weighs a fragile 550 kilos as she hurtles into the dust cloud.
Well, you can see there, if we can show you the picture, the flight dynamics picture coming from Darmstadt itself, with just over 50,000 kilometers to go and 12 minutes and 20 seconds to go to the time of closest approach. Let me go back to our guest. I was talking while that film was running there to Professor Meadows again about the fact that we've heard that there are approximately, well, they said that they've had 50 medium-sized impacts that have punctured the exterior shield, and that those things are coming through about 1 every 10 seconds. Is it another case of you saying, well, yes, that might well be, how do I know?
Well, I think it's building up very nicely. With any luck, we could have a disaster in a quarter of an hour.
But I mean, I've heard I've heard figures bandied around that, I mean, even by Tony MacDonald, who's the head of the dust impact experiment, talking in terms of things like 10,000 impacts a second. We're a long way from that if it's one every 10 seconds, aren't
Absolutely. The thing you have to remember, and I'm sure you do, James, is the size of the impact. This is the vital thing. If you're really talking a number of impacts, there are probably tens of thousands of very tiny things hitting it and have been doing for a long time back. Really tiny things. It depends what size range you're talking about. And as you come in towards the comet, all the evidences are that the size distribution, the upper end builds up.
The bigger?
The bigger bits build up, you see.
But you're talking about what we've got up in space, although it takes a few minutes for the information to get down to us in the form of data or pictures. We're talking about closest encounter point in 4 minutes, just about, aren't we? Oh no, sorry, 11 minutes, I beg your pardon.
11 minutes.
My clock. About 44,000 kilometres.
You have to remember that there's 10 minutes transmission time, isn't there?
That's true, yes.
You know, things can disappear and you don't know about them for a while. We'll have to wait and see. But no, at the moment, the build-up is the models assume that there is a distribution that falls off in a generally similar way in all directions from the comet. That's what the models which have been quoted assume. Now, the problem is that that doesn't happen. It falls off differently in different directions, so it depends what way you're going past.
Yes. So, I mean, everything seems to point to the fact that we have no idea no one has any idea what's going to happen in the last few minutes before closest encounter, because the rates will change radically.
But if we could predict what would happen, there wouldn't be any point in us sitting here.
Yes, I suppose so. Yes. Let's go back to our impact. Well, now you see that we're getting this, finally getting this computer-generated data coming back in about the amount of damage that's going on here. And Tony MacDonald, I gather you're out there talking with Patrick right now. Are things hotting up for you, or are you still as happy as you were?
Well, very much so. Well, they are now within a minute or so of closest approach, and we're very glad that Tony MacDonald has taken time off at this particular moment to come and join us. Tony, very near the crisis now. What's the situation?
Well, we're a little bit behind in terms of information coming back, of course. The probe is actually at its probably worst position now, but in fact the data's 12 minutes behind. The data's building up. We know that the shield is lasting. In fact, it's going to survive, and I think the chances for getting past and getting data on the way out are very, very good.
You are, in fact, do you think, are now over the worst period?
I think we are indeed, yes.
So, in fact, the shield has really done all and more than was expected of it.
Superb indeed, yes. The dust cloud is, though, very much smaller than we'd anticipated.
Very much smaller, or just marginally so?
Perhaps a factor of 2 smaller.
And what about the actual distance of the dust from the nucleus? Is that smaller as well?
Yes, indeed, yes. It took us, indeed, at least an hour before we got our first impact, so very much smaller.
Have you had any major impacts at all on the spacecraft?
Not any which have rocked the spacecraft in any way, and therefore the stability of the spacecraft is good. It's going on the same course, good pointing direction, the camera will get good images.
Well, as we know, you know better than I do, the bumper shield is designed in 2 parts. A thin one to break the emitted particles up and produce them into a kind of a spray, and has that principle really paid off?
We've got to evaluate the data before we can really confirm it, but yes, indeed, it looks as if it's doing very well at the moment.
What about the numbers of really large particles? In view of the fact that Giotto has escaped so far, do you think they really are much rarer than was expected?
Well, at this time, the largest particle probably has indeed struck the comet, the space probe indeed, but we don't know yet. We've got to wait 6 minutes for that information.
We have indeed. And, of course, you're not quite out of the wood yet, or rather out of the dust storm, because you may be just about passing closer to approach now, but then there's the outward journey. Do you think there's any danger of being struck on the outward journey?
That's supposed to be, I think, an easier ride than the inward journey. The comet is a bit shorter on that side because of our approach direction.
And, in fact, well, therefore, it does seem that all is going to go well.
I think so.
Well, Tony, thank you very much.
A pleasure.
And, in fact, we have here got pictures of the control room where everything at the moment is going on. After all, this, is the nerve centre of the entire operation, as you can see. And you can see their picture on the control room screen coming in from Giotto. At the moment, it all seems to be going well, and I imagine there's rather a feeling of considerable relief down there at the moment, because if all the indications are as we believe, then Giotto will in fact survive the encounter and will be able to pass on to possibly to other comets, which is probably something that most people, well, everybody wished, but I don't think people were entirely confident about right up to the last moment. So I imagine down there now that there's all kinds of discussions going on, and the revelation that the dust cloud is smaller than we expected really is, I think, very much of a surprise, because after all, Halley's comet's always been regarded as a very active comet. It's a large comet. It's a very large comet, and we are now just about at closest approach. But, of course, remember, the distance of the comet and the probe from us at the present moment is something like 150 million kilometers. And that's just about the same distance as the distance between the Earth and the Sun. And light and radio waves and messages take something just over 8 minutes to cover that distance. So take 8 minutes to cover that distance. And so it won't be for another 7 or 8 minutes that we'll know whether Giotto really has survived. But all the indications are that it has. James.
Yeah, well, here in Greenwich, we're about to see some of the pictures that have been coming in. And perhaps I could ask you, Alec, to start commenting on what you think they're telling us. Can you see enough at all?
Well, it's difficult to really appreciate what one sees in a picture of this nature. It's in false colour. The brightest bit is the red bit, and that looks quite small, but I can't tell you exactly how big it is. That has to be really processed properly. But the pictures look of very high quality indeed.
Do you think that might be because of this business about their having gone through perhaps the sort of last major shell of dust and got themselves into, as it were, a clearer zone?
Well, they certainly look a lot clearer than they did before, and a lot more compact there in the middle, and if anything, you'd expect it to be larger being closer. So I guess that is what's happening, that the dust is clearing, so to speak, and we're seeing further into the nucleus than before. Maybe we are seeing the actual nucleus, but it's hard to say at the moment.
Yeah, the point is, of course, these pictures are pictures that have come in some minutes ago. They're not, in fact, as we can see, we're 21,000 kilometres to the point of closest encounter. In fact, these pictures may have come from how far back? How long do you think it would take them to get these pictures processed to that stage and on this screen?
Well, the light travel time is about 8 minutes, and it'll take a few more minutes perhaps to come out on the screen like that.
To that, so those pictures you reckon could be anything about 15 minutes back?
Yes.
The quality of those pictures, Jim, does that mean that you stand a better chance of getting the kind of analysis you need than there would have been if the dust had been higher than was expected? Oh, sorry, yes, if there's been a lot of dust?
It means that Giotto has a much better chance of getting right through, yes, than we would have said perhaps an hour ago.
What about this business of the Russians saying, Jack, that they thought that there might have been a very dense cloud of dust just above the surface of the nucleus? Did I not hear that claim?
You did indeed, yes. That's the interpretation. They produced slightly different interpretations from the two Vega spacecraft, which went through a few days after each other, but about the same distance away. But the interpretation they put forward after the second one was that there was a cloud, an egg-shaped nucleus, about 6 kilometers across, so a bit less than 5 miles. But what they were seeing, they thought, was a dust cloud around a real solid nucleus, which was perhaps 2/3 to a half that size. Yes. Now, if that's the case, we really are in serious problems, because one of the great things we expected to get out of this was a solid nucleus.
I'm sorry to interrupt you, because these are live pictures coming down from Giotto now. Alec?
Well, it's progressing, that's as far as one can really judge it from those pictures. They look like they've got more structure than they had before.
What does that mean, they have more structure?
Well, that means we're seeing more detail. We're getting closer, and we'd expect to see more detail, but I think we can see rather gross structure. And, of course, the nucleus would not be uniformly white ice, a uniformly white ice ball or something like that. It would be very murky and dust and grey in places and so on. That's what looks like we're seeing. If we're seeing the nucleus, I'm not suggesting we are, of course.
No. Can I ask you, the general blob, presumably the blob to the top left there is a dust or some artificially created thing, but the general blob that we're looking at, the orange-coloured blob with the core, approximately how big across would that be if you were, say, seeing pictures that came in that were taken 8 minutes ago and therefore, say, about 50,000 kilometres out? Do you want to make a guess?
I can't make a guess, I'm afraid. And it's difficult anyway, because those are contours we're seeing, and we can't really make out which contours we see.
Sorry, maybe I should ask the question more clearly. Are we actually seeing well inside the head of the comet that we would normally see if we looked up on a clear night and saw it? I mean, we're looking at it well inside that, are we?
Yes, we're certainly looking well inside it. But just how far inside, it's very difficult to say from those pictures.
Yes, right. Let me go back to Darmstadt with Patrick. Patrick.
Well, we're delighted that Alan Johnson to be able to join us again. Well, Alan, this is the great moment. What do you make of it?
Well, it's been very exciting. We've got some very interesting data. We've just seen the ions disappear from the view of our instrument, and so that means we're inside the contact surface very close to the comet. And we're now just seeing the final pictures from the nucleus.
We really are seeing the nucleus itself, you think?
I don't know. We'll have to wait until we see the pictures in more detail before we can tell exactly what part of it is the nucleus.
It seemed to be irregular in shape, and that could, I suppose, tie in with the results obtained earlier on by the Vegas.
Yes, I'd expect it to be irregular in shape. Certainly, it's always been thought of as probably irregular, and that's the picture that's coming through now.
Does that give you any clue as to why one side of the comet is so active and the other apparently passive?
Not yet, I think. If it's irregular, it certainly tells us it's not a uniform body, but to tell exactly why the reasons are that one side is active and the other side is quiet is beyond us at the moment, I think.
Well, when we came on the air, we said that we hoped that just after midnight we would be able to see the actual nucleus of the comet. All in all, do you think we've done that?
I don't know. We'll have to wait and see.
Gentlemen, can I interrupt because... Hello, this is James in London.
Getting some very interesting
Can I interrupt because I hear that we're getting live pictures in from the dust detecting equipment from the experiment, looking at what's happening to the shields at the moment, and you can see there the impacts actually being generated in real time.
Is that going to be a problem, do you think?
Waiting to see.
This is... we're not sure what that picture is there. That obviously it looks like something coming down from the camera, but why it's coming in that particular format. I don't know. Alec Boxenberg, do you want to guess about that?
I think there's some interference there that is making it very confusing for us.
Do you think it's skewed off at all, or...?
No, definitely not skewed.
Jim Cohn?
I wouldn't like to say at this stage.
You don't know? As you can see, yes, the time is building, so we've passed closest to the point of closest encounter. The spacecraft evidently, well, you can see how fast it's moving. It went in through 540, and evidently it seems to have survived. Since the pictures, since our timing is presumably timing based on how long it takes for the pictures to get here, the pictures are here, therefore it must have survived. Now, Jack, they were talking earlier about the fact that it has to go out the other side.
Yep.
Sorry, let me go to Lee Sproat, our youngest amateur astronomer over there, who's shaking his head when I say we think it must have survived. Why are you shaking your head, Lee?
I don't think it will survive because as you're starting to go into the comet's nucleus each time, the speed of the particles is increasing by about 100-fold. And the images that were coming off the television there were very distorted, so I think that something's either happened to the probe itself or something's happened to the camera.
Yes. Well, let's go back and check on what they think in Darmstadt about that. Patrick?
Yes? Well, I don't know. What do you think about that one, Alan?
Well, I'm still waiting to see whether it survived or not. I think that's my biggest concern at the moment, because we're hoping to collect data on the way out.
It'll be absolutely ironical, won't it, if it's destroyed at the very last moment.
Yes, but it was part of the plan that it might be destroyed at the last minute, and so we're not disappointed if it is.
Well, I think everyone is going to be extremely disappointed. Well, as we're also being joined now by Dr. Leonard Culhane, who's the director of the Mullard Space Science Laboratory. Leonard, what do you think about this?
Well, a superb evening for Europe and of course, for Mullard Space Science. And I think half the job is done if we've seen the action on the way in, and Alan's instrument has functioned superbly, and we have a lot of data in the can.
What about the survival of Giotto? Are you still confident now?
Well, right now, who can tell? It doesn't look so likely, but we at least have acquired a lot of data as we approach the nucleus, so we're very pleased with the evening's work.
I wonder how long it'll be before we know, in fact, whether Giotto has survived or not, because after all, closest approaches, well, it was passed some time ago, and it took place at 11 minutes past midnight our time, so it's quite definitely past now, and the signal should have come back, and apparently don't seem to be getting any at the moment.
We seem to have lost them just at the moment.
We seem to have lost them at the moment. That could be one of several things. It could be, could it not, that Giotto has been struck by some kind of particle that has very slightly jolted the high-gain antenna out of its path. And if it's tilted by as much as 1 degree, then we actually lose the signal.
Exactly so. And the time to recover from this is like 1 hour, I believe. Is that correct, Alan?
Yes, something like an hour or more.
So if we don't get any more signals from Giotto for the next hour or so, it's still too early to say it's definitely been destroyed.
Indeed.
That's right.
Indeed.
Yes.
If you had to bet on it, what would you say is the more likely? That it has in fact been destroyed or put permanently out of action by a sizable impact, or that it has been jolted out of a line, shall we say?
Jolted out of line is the more likely, definitely.
I think that's right. I certainly hope that's right.
Is there any possible way of finding out at the present moment, or do we have to simply wait and see whether the signal is reacquired?
Well, if they know if they watch what happened in the control centre, they will have some idea of whether it started to tilt first before they lost the signal, or whether they disappeared suddenly. If it disappeared suddenly, then it's probably a destructive impact. But if it starts to tilt off first, then it could be just the tilting of the thing.
Well, I can see there's some pictures actually from the control room for the people there, and they seem to get known to be rather puzzled.
Yes, well, they've got a lot of procedures to go through to check out exactly what's happening, and they have a procedure worked out by which they're going to do this.
If by any chance we don't get any more signals from Giotto, you would still say that your particular experiment has been a success?
Yes. Absolutely, indeed.
And how long will it take you to evaluate the data that you've got?
Well, I would think about 2 years, at least.
Oh, there's a new picture coming in, I think. A new picture coming up, so this...
Action again.
Now, I wonder whether that's an actual picture in real time, or whether it was one transmitted a few minutes ago. I think it's one transmitted a little earlier. It looks very similar to that picture that we saw earlier on. I don't think that's coming on live from Giotto, do you?
No, it doesn't look like it. It looks like it's been more processed.
Well, we can see there that curious shape of the nucleus again. Not exactly a double nucleus, and the Vega 2 pictures did strongly indicate that there was a real double aspect there, and you don't see that on that particular picture.
That might be due to the particular angle from which you're looking at it. If we're looking at it end-on, that double aspect might disappear.
I wonder.
Patrick, while you've been talking there, we've been listening directly to the people in flight dynamics now, and of course in the dust experiment, and I gather that they have recently gone through, in the last few minutes, several hundreds of impacts per second, and it might well be that that's what we saw changing the quality of the picture, altering the quality of the picture in some way as we came through, and that perhaps having gone through that, it's now steadied and cleared up again, if that were indeed a live picture that we caught, which looked so clear just now. What's your feeling about that over there?
Well, we don't think it was a live picture, but it's very difficult to tell. What do you think, Leonard?
It certainly doesn't seem live to me at the moment, and I suppose the worst may have happened. Who knows? Alan, what do you think?
Well, I'm trying to look up there on the monitor screen to see if that tells us anything about it. We can see some signals coming through from the control center at the moment, and it seems to indicate the TM quality is good. And that may mean that they've got the link back, but maybe it's too soon to tell that.
If by any chance there has been an impact which has just jolted the high-gain antenna to one side, so the signal is now missing us, what is the very minimum time that it would take for us to reacquire the signal?
I don't know. I think it's probably something like several hundred seconds. That would be perhaps as much as 15 minutes. Because it has to take time for the wobble to be damped out.
Could I interrupt, gentlemen? Could I interrupt, gentlemen, to ask you what it is we're watching now? In that case,
at the present moment,
yes, this particular picture.
Well, it certainly is a detailed picture. It's an enhanced picture, but it is an enhanced picture of the nucleus area, obviously, and that's really what makes me feel that it was probably transmitted a few minutes ago. I don't think that's coming down live because it's too obviously enhanced.
Yes.
And I would say that that was probably taken almost at the point of closest approach when we know that Giotto was still functioning. Would you agree on that, Leonard?
Yes, that seems reasonable view, Patrick.
And once again, we can see the curious irregular shape there, and we have got what looks to be a well-defined central portion, and I just wonder what they can make of that one. Of course, we've simply got to wait and see what happens now, because if we don't get any more signals from Giotto, then one very sad result is that we lose all the data we would have got from the outward journey, and we would, of course, lose also the pictures we would have got from the outward journey.
Yes, from my point of view, I think it's possible that the contrast between the outward journey and the inward journey would have provided us with a great deal of information that we don't get from just going in on one side, because of the particular asymmetries caused by the magnetic field.
Patrick, we hear from Darmstadt, while you were talking there, that they seem to have lost contact. They seem to be getting no more telemetry from the spacecraft. So it does sound as if the speculation there that you were indulging in about the spacecraft having been slightly knocked off course may have, in fact, happened, since the last report I heard a few seconds ago was that there was no telemetry coming down.
Well, we very much hope in a way that that is so, because, I mean, one of two things has happened. I mean, disregarding a straightforward instrument failure on board the spacecraft, which at this juncture I think is extremely unlikely. It's some outside influence, all right, so it can really be only one of two things, or rather one of three things. It could be that an impact has put the camera out of action. It could be that an impact has put the entire spacecraft out of action or even destroyed it. Or it could be that the antenna is now misaligned. And I think everyone's going to hope devoutly that that in fact is what has happened, because if so, there's every chance that we shall be able to reacquire the signal in a period ranging from something like 15 minutes, and it happened several minutes ago now, which could be any moment, I suppose, up to an hour. And if that is so, then all may not be lost. But of course, the further away Giotto is, the less information it's going to send back, and once it's been past the nucleus for an hour, then it's going to be back well outside the main region, and we really shan't get a lot more information from it. I think that's a fair statement, isn't it, Anna?
Yes, that's true, yes.
We
need to, the most interesting information comes from the last 100,000 kilometres.
We've got, back here in London, we've managed to put together the computer-generated data from the latest information before the loss of signal on the DID, that's the dust impact experiment. And it does seem that there was a fair pile of it in those few minutes back, what, 10 minutes ago, when they were talking about having had a surge, which might well be the reason why the spacecraft was knocked off course and we lost the signal. I was talking while Patrick was having a discussion there on the air with one of our guests here, who of course made the rather important point that whether the spacecraft signals were cut off suddenly or not, or faded in any measurable way, but of course it was Colin Ronan. Let me ask you to explain what you meant by that, Colin.
Well, it was just that if it's knocked off course, and not destroyed, if the antenna moved away from off a degree, then the signal should fade away. Whereas if the whole device was smashed into by a large particle, then you get a sudden cessation of all signals.
Well, either way, ladies and gentlemen, whatever reason we're no longer getting signals, obviously some magnificent data has been collected, and there's a man with Patrick now who no doubt everybody is waiting to hear from, Fred Whipple, the father of cometry himself.
And after all, who better to join us at this critical juncture than Fred Whipple, the man who worked out the dirty snowball theory of the comet? Well, Fred, you said earlier on that we were going to see the nucleus tonight. Did we?
We did. I'm quite sure we did, yes.
It was, in fact, that red mass that we saw on the screen.
Well, it will have to be analyzed in more detail without all of those pretty colors, which may mislead the public as to the nature of a comet nucleus, because it's really a very black, gray, like perhaps black velvet or charcoal.
Well, we have emphasized all the way through this program that these colors are not genuine. You don't really see a comet like that. But from those pictures, what can you tell about the composition of the nucleus? Can you think you can definitely confirm finally your dirty snowball theory?
Well, I think that we have enough evidence that will come out of the spectroscopic evidence, the nature of the gases, and the analysis of the dust to show it conclusively. Yes.
Of course, it's not only the camera, as we know. I mean, the camera did magnificently right up to the time of closest encounter.
Yes.
Now, I imagine those last pictures that actually came back from Giotto were taken just about the time, and it was something like 540 kilometers away from the nucleus itself.
Or perhaps a little farther than that, but perhaps 1,000 kilometers, but something of that order.
But of course, it's not only those pictures that will help to confirm your theories, all the other experiments as well. Which do you think are the most important of those from your point of view?
Well, I don't know. There's several of them, of course, and but I think the one that tells the composition of the gas will be in the final, when the final story is told, will be the most important.
Well, now come back to the matter of the moment. We have lost all trace of Giotto. What do you think has happened? Has the spacecraft been destroyed? Is it the cameras been put out of action? Or has the antenna been jolted so that at the present moment we are not receiving the signals?
Well, I don't think at this point I can answer that question. I think that will be a technical question. But I'm sure that the dust in the neighborhood of the nucleus did it, and shows that comets are very dangerous when you go through them at 70 kilometers per second.
That's very right. But at least it's proved what you wanted. Fred Whipple, thank you very much. James.
Well, back here we've got somebody on the telephone in the United States who might have a few interesting remarks to make, given the fact that he's the only man to have, as it were, taken a spacecraft through similar circumstances, though not quite in the same way and not as close. Bob Farquhar, who's in the United States on the phone at the moment, was in charge of being able to put that spacecraft I mentioned to you before, ICEY it was called, through the tail of a comet called Giacobini-Zinner some time back. Bob, how are you reacting to what's been happening tonight, particularly in terms of the experience with the dust?
Well, actually, I was very thrilled to watch the encounter. I only wish that we could have played a more important role.
We're getting Bob too well there. You can get stuff from Giotto healthily enough, but no.
I think that the Giotto flyby is going to be one of the great successes of all time as far as spaceflight is concerned.
You said when ICEY came through the tail, maybe comets don't have too much dust around them anyway. How do you feel about that in the light of what's happened tonight?
Well, obviously, different comets have different amounts of dust. I think one of the things that we're going to try to do in the future is to collect some of this dust, but we're going to have to go a heck of a lot slower than Giotto did. And we also can't get too close to large comets like Halley. I think one of the interesting things that I heard was that the bow shock time of detection wasn't that far different from what we found at Giacobini-Zinner. I thought that was kind of odd because I think that the activity of the two comets are quite different.
Yeah, what would it indicate to you, the fact that we lost telemetry? Do you think it's possible that perhaps after if Giotto has survived, if it comes out of the dust cloud, it could go back perhaps onto the automatic reacquisition of proper attitude and get back into control, into contact with us? Is such a thing possible?
Yes, I think that there is some hope that the spacecraft has survived the encounter, and that maybe we just lost lock with the antenna as some dust particles hit it and knocked it off of the pointing towards the Earth. I'm very hopeful of that because I've been working with Rudiger Reinhardt to look for ways to target Giotto back to the Earth so we can do a swing by of the Earth and then onto another comet.
Yeah, there were always plans that, you know, if Giotto survived, that it would do the same thing, and it would move off elsewhere, and we'll wish it luck, and we'll obviously not know until sometime in the middle of the night whether or not they've managed to reacquire the signal. Thank you very much indeed for talking to us, Bob. We've got now the first real enhanced picture available from the spacecraft. There you can see it. And would you care to comment on that, Alec?
Yes, I think it's a remarkable picture. There's clearly a lot of irregularity in the nuclear region there, and also a lot of surface structure that we saw before. It's much easier to see it in this picture that we're seeing now. But of course, we still have to, as has been said by many others, massage it further, and of course we can't really make out exactly where we are in the nucleus because the colour boundaries are a little bit confusing.
But sorry, you're saying where we are in the nucleus. You mean a large part of this picture could represent the nucleus itself?
Yes, most definitely.
In other words, we are looking at a partial view of the entire nucleus, you think?
No, I think they're seeing the nucleus within that picture, and it's probably in the area of the green part of the frame that you're seeing. But just where it comes in depends very much on where the colour boundaries are placed, and that is a matter of massaging. We'd see it more easily if it were black and white, but then we wouldn't see the whole depth of the image, and that's why we're seeing it in this false colour now.
Let me go back to Jack Meadows. One of the things that they said before they went was that if they got close enough and the camera worked, they would be able to see features on the surface of the nucleus, presumably after massaging the pictures, down to as small as, 150 feet across?
Yes.
Now,
well, I think
what would you have seen in
150 metres, but perhaps 150 feet. Never mind. Yes, sorry.
Oh, I've just heard we've got some new information from Patrick. Excuse me, let me go back to Darmstadt.
Yes, indeed. It's rather encouraging news, and this comes from Parkes in Australia, the main receiving station. Apparently, there are being signals received now from Giotto. They're very weak and they're fluctuating, and they can't at the present moment give a picture. But the fact that they are being received at all indicates that probably the spacecraft has not been destroyed, and that our conjecture earlier on that it was in fact an impact which thrust the antenna to one side and made the signal miss the Earth is probably the right one. And if that is so, all the indications are that we may reacquire Giotto again in something like 15 to 20 minutes. Well, of course, then it's going to be well away from closest approach, but it still should be enough to send back some data on the outward journey, if that is true. We can't be absolutely certain yet, but I'm glad to say that it is starting to look as if, after all, Giotto has not been destroyed. It has indeed survived. And so, even if Giotto hasn't survived, and I think it has, in fact, we've learnt a great deal. It has been a remarkably successful, very successful mission in all respects. It was the first attempt to probe the nucleus of the comet, and it has done so. We think we've actually seen the nucleus. It's paved the way for future probes. But don't forget also that even though encounter is now past, and whether Giotto has survived or not, there's still a great deal of work to be done. We've had the raw data. They've now got to be processed, analysed, and worked over. And I estimate this is going to take a whole team of scientists, many months, probably a couple of years, and it may be at least 2 years before we get the final results of Giotto. But whether or not we're going to get any more detail, there's no doubt whatsoever that Giotto has been an outstanding success. And I think it's going to be remembered as long as space history lasts. And so, for the moment, from Darmstadt, good night.
And here in London, as Francis and his guests have watched through this evening, I think we've all been aware that it was quite an extraordinary event. As Jack Meadows said earlier on, the important thing was that nothing happened for a long time, and then everything happened. And as you saw, everything happened, and possibly for a certain amount of time, even the destruction of the spacecraft. That now looks as if it may survive, may come out the other side of the coma, and survive to visit another comet, because I understand that it still has plenty of fuel on board. So that brings us to the end of our program. I hope you enjoyed it as much as we did. I hope you enjoyed going through the same process that the scientists went through, the long build-up to the short but highly intense results. And over in Darmstadt, you can see that the scientists are feeling pretty much the same way, as everybody who's been involved in this mission from the beginning, because, after all, literally speaking, the encounter with Halley has been, for everyone concerned, well, almost everyone concerned, except perhaps the youngest people watching, and indeed one of our guests here tonight, it has been, for everybody concerned, literally a once-in-a-lifetime experience. There will not be another encounter with Halley program for another 76 years. So, on that note, good night.
Well, comets may come and go, but just before we close, we'll bring you back to Earth with the weather forecast. And rain will die out from Northern Ireland and Western Scotland early in the morning, with sunny periods developing, but there'll be a few showers. Eastern Scotland and northeast England will have a little rain at times, but it will brighten up as the day